As you settle in tonight, let the worries of your day dissolve into the darkness around you. The room fades away, and in its place comes a vast, infinite canvas of possibility. Tonight, we journey not across oceans or continents, but through the boundless realms of the cosmos itself. A journey without passports or limitations, where the only requirement is your curiosity and willingness to wander. The universe spreads out before us, an endless tapestry of light and shadow that extends in every direction. But what does it mean for something to be truly infinite? Can the universe have an edge, a boundary, where everything simply stops? These questions have haunted human minds since we first looked upward at the night sky, seeking meaning in the scattered diamonds of light overhead. Imagine floating in space, far from any planet or star. You drift outward, past our solar system, beyond our galaxy, through the vast intergalactic voids. No matter how far you travel, no matter how many billions of light years you cross, you would never encounter a wall with a sign declaring "Universe ends here." There is no physical boundary we know of, no cosmic shoreline, where the universe stops and something else begins. The universe we can observe, all the galaxies, stars, and matter visible to our instruments, spans roughly 93 billion light-years across. Not a million, not a billion, but 93 billion light-years. Each light-year represents the distance light travels in a single Earth year, nearly 6 trillion miles. To put this scale into perspective, if you could somehow travel at the speed of light, it would take 93 billion years to cross the observable universe from one edge to the other. By then, our sun would have burned out many times over. Earth itself would be long gone, yet you would have traversed only what we can see. But this observable universe is merely our cosmic horizon, the limit of what light has had time to reach us since the beginning. Like standing in a dark field with a lantern, you can only see as far as your light extends. Beyond that circle of illumination lies more darkness, more field, unseen but no less real. Similarly, beyond our observable bubble lies more universe, possibly infinite, stretching endlessly in every direction. The very space in which galaxies are embedded has been expanding since the birth of the universe nearly 14 billion years ago, not expanding into anything. There is no outside for the universe to expand into. Rather, space itself stretches, carrying galaxies along like raisins in a rising loaf of bread. The farther away a galaxy is, the faster it appears to recede from us, not because it's moving through space, but because the space between us is growing. This expansion began with an event of unimaginable energy and density called the Big Bang. Not an explosion in space, but an expansion of space itself. In the first trillionth of a second, the universe underwent a period of exponential growth called inflation, expanding faster than the speed of light. This rapid growth smoothed out irregularities, like stretching a wrinkled bedsheet, and seeded the structures we see today. Everywhere we look in the cosmos, we see a remarkable uniformity. The same physical laws apply. The same types of galaxies form. The same elements exist in the same proportions. This homogeneity suggests that all of the observable universe once occupied an infinitesimally small region before inflation stretched it to cosmic scales. The cosmos remembers its shared origin in its consistent nature. When we look deep into space, we also look back in time. The light from distant galaxies has traveled for billions of years to reach our telescopes, showing us not how these galaxies appear now, but how they looked in the ancient past. The most distant light we can detect comes from the cosmic microwave background, the afterglow of the Big Bang itself, released when the universe was just 380,000 years old. This ancient light surrounds us in all directions, a uniform glow that has cooled over time to just 3 degrees above absolute zero. Beyond this cosmic microwave background lies a region we cannot directly observe, the epoch when the universe was so hot and dense that light could not travel freely. This cosmic dark age lasted for hundreds of millions of years until the first stars ignited and began to illuminate the cosmos once more. Those first stars were nothing like the ones we see today, massive, brilliant, and short-lived. They forged the first heavy elements and seeded the universe with the building blocks of planets and, eventually, life. As we drift further from Earth in our mind's journey, we pass through our local neighborhood of galaxies. Our Milky Way is just one of more than 50 galaxies bound together by gravity in what astronomers call the local group. This collection includes the majestic Andromeda galaxy, slightly larger than our own, and countless smaller dwarf galaxies orbiting like cosmic fireflies. In about 4 billion years, the Milky Way and Andromeda will collide, their stars passing harmlessly by one another as the galaxies merge into a single, larger system. The local group, in turn, is just one small cluster within the Virgo supercluster, a vast complex of galaxy groups and clusters spanning more than 100 million light-years. And the Virgo supercluster is merely one lobe of an even larger structure called Laniakea, a name derived from Hawaiian words meaning immense heaven. This immense heaven contains over 100,000 galaxies, their combined mass equivalent to 100 quadrillion suns. These superclusters form a cosmic web with galaxies concentrated along filaments and walls surrounding vast empty regions called voids. These voids are not truly empty, they contain sparse galaxies and invisible dark matter, but compared to the dense filaments that surround them, they appear as cosmic deserts. The largest known void, called the Botes void, spans about 330 million light-years, a region so empty that if our Milky Way were placed at its center, we would not have discovered other galaxies until the 1950s. The cosmic web itself is the largest known structure in the universe, a network of interconnected filaments that stretches across billions of light-years. Computer simulations suggest that this web-like arrangement emerges naturally from the action of gravity on the nearly uniform matter of the early universe, like water droplets forming patterns on a spider's web. The dark matter, invisible to our telescopes but detectable through its gravitational effects, forms the scaffolding upon which ordinary matter, the stars, planets, and galaxies, collects. Dark matter makes up roughly 27% of the universe's contents. Ordinary matter, all the stars, planets, dust, and gas we can see, accounts for just 5%. The remaining 68% consists of an even more mysterious substance called dark energy, which acts as a kind of anti-gravity, pushing the universe apart rather than pulling it together. This dark energy is causing the expansion of the universe to accelerate, driving galaxies away from each other at an ever-increasing rate. If dark energy continues to dominate, the universe will expand forever, growing ever more vast and empty. Galaxies beyond our local group will recede beyond our cosmic horizon, their light stretched to invisibility by the expanding space between us. In the far future, trillions of years from now, observers in our galaxy would see only darkness beyond our local neighborhood, unaware of the rich cosmic history that once filled their sky. But our journey tonight takes us not just across space, but across possibilities. Perhaps what we call our universe is merely one bubble in a vast cosmic foam, a multiverse of separate, distinct universes, each with its own physical laws, constants, and dimensions. Perhaps new universes are constantly being born, inflating from tiny quantum fluctuations into entire cosmic realms. Perhaps our universe, vast as it seems to us, is merely an infinitesimal speck in a much larger, much older, much stranger reality. These ideas are not mere speculations, but emerge from serious physical theories that attempt to explain the properties of our observable cosmos. String theory, for instance, suggests that our universe may be one of up to 10 to the power of 500 distinct possible universes, each with different physical constants and properties. That number, 10 followed by 500 zeros, is vastly larger than the number of atoms in the observable universe. Imagine wandering through this garden of cosmic possibilities. In one universe, the force of gravity might be slightly stronger, causing stars to burn brighter and die faster. In another, the electromagnetic force might be weaker, preventing atoms from forming stable structures. In most of these possible universes, life as we know it could not exist. The delicate balance of forces that allows for stable stars, planets, and complex chemistry might be exceedingly rare in the vast landscape of possible universes. This observation has led some to formulate what's called the anthropic principle, the idea that the physical properties of our universe must be compatible with the conscious life that observes it. Of course they must be, for if they weren't, we wouldn't be here to notice. Whether this apparent fine-tuning is merely a cosmic coincidence, the result of a multiverse generating all possible universes, or evidence of some deeper principle, remains one of the greatest mysteries in modern cosmology. As we float through the immensity of space in our mind's journey, we might wonder, is infinity itself truly comprehensible to finite beings like ourselves? Can we genuinely understand something without limits, without boundaries, without end? Perhaps the concept of infinity is less a description of a physical reality and more a mathematical abstraction, a useful tool for understanding a universe that, while immense beyond human scales, might not be truly infinite. Consider a balloon being inflated. An ant walking on its surface might perceive that surface as infinite. It can walk forever without reaching an edge. Yet the balloon's surface is finite, merely curved back upon itself. In a similar way, our universe might be finite yet unbounded, its space curved in higher dimensions we cannot directly perceive. If you could travel far enough in one direction, you might eventually return to your starting point, having circumnavigated the cosmos itself. Einstein's general theory of relativity tells us that space and time are not fixed and absolute, but flexible and dynamic, warped by the presence of mass and energy. Massive objects like stars and black holes create curves in space-time, like heavy balls placed on a rubber sheet. Light follows these curves, allowing gravity to bend its path, an effect first confirmed during a solar eclipse in 1919, when stars appeared to shift position as their light passed near the Sun. This curvature extends to the entire universe. Depending on the total amount of mass and energy it contains, the universe could be positively curved like a sphere, negatively curved like a saddle, or perfectly flat. Current measurements suggest that our universe is remarkably flat, another consequence of cosmic inflation, which would have stretched any initial curvature to near perfect flatness, just as inflating a balloon makes its surface appear increasingly flat to an ant walking upon it. If the universe is precisely flat, it may indeed be infinite in extent. If it has even the slightest positive curvature, it would be finite but unbounded, like the surface of a hypersphere. If it has negative curvature, it would be infinite but with a complex, saddle-like geometry. Our current measurements cannot distinguish between these possibilities with perfect certainty, leaving the question of the universe's spatial infinity unresolved. But infinity emerges in our cosmic story in other ways as well. Consider black holes, regions where matter has collapsed to such extreme density that nothing, not even light, can escape their gravitational pull. At the center of a black hole, our current theories predict a singularity, a point of infinite density and infinitely curved space-time. Here, the equations of general relativity break down, suggesting that a more comprehensive theory, perhaps uniting gravity with quantum mechanics, is needed to fully understand these cosmic extremes. Quantum mechanics itself introduces a different kind of infinity into our cosmic picture, the infinity of possibility. At the smallest scales, reality becomes fuzzy and probabilistic rather than definite and deterministic. Particles exist in multiple states simultaneously until measured, and empty space itself is not truly empty but seething with virtual particles that briefly flash into existence before disappearing again. This quantum foam may be the ultimate source of all cosmic structures, the seeds from which galaxies and stars eventually grew. In the earliest moments of the universe, quantum fluctuations, tiny variations in energy density, were stretched to cosmic scales by inflation, creating the slight irregularities that would eventually become galaxies and galaxy clusters. What began as microscopic variations became the vast cosmic web we observe today. This connection between the infinitesimally small and the infinitely large is one of the most profound aspects of modern cosmology. The recognition that the largest structures in the universe emerged from quantum fluctuations smaller than an atom. As we continue our mental journey through the cosmos, we encounter the concept of cosmic horizons, boundaries not of space itself, but of what we can observe. The cosmic horizon represents the maximum distance from which light has had time to reach us since the beginning of the universe. Beyond this horizon lie regions we cannot see, not because they don't exist, but because their light has not yet had time to reach us. Due to the expansion of space, this cosmic horizon is not fixed at 14 billion light-years, the age of the universe, but extends to about 46 billion light-years in all directions. Light from more distant regions will never reach us, as the expansion of space carries them away faster than their light can travel toward us. These regions exist, but are forever beyond our observational reach, hidden behind a cosmic curtain drawn by the mathematics of expansion. This horizon is not static but dynamic, growing larger as the universe ages. With each passing second, light from slightly more distant regions reaches us for the first time, revealing a bit more of the cosmic tapestry. Yet paradoxically, as the universe expands at an accelerating rate, there are regions whose light, though currently visible to us, will eventually fade from view as those regions recede beyond our horizon. The observable universe of the far future will be smaller than it is today, limited to those galaxies bound together by gravity into local clusters. Galaxies themselves are islands of stars in the vast cosmic ocean, each containing billions or even trillions of stars. Our own Milky Way holds more than 200 billion stars, arranged in a flat disk with spiral arms, surrounded by a spherical halo of older stars. This structure emerged gradually over billions of years as gravity drew together clouds of hydrogen and helium left over from the Big Bang. The first stars formed roughly 200 million years after the Big Bang, igniting nuclear fusion in their cores and illuminating the universe for the first time since its fiery birth. These early stars were giants, perhaps hundreds of times more massive than our Sun, burning hot and bright for just a few million years before exploding as supernovae. In their brief lives and spectacular deaths, they forged the first heavy elements, carbon, oxygen, iron and more, enriching the cosmic environment and making possible the diverse chemistry that would eventually lead to planets and life. Successive generations of stars continued this process of elemental creation, each generation forming from clouds already enriched by its predecessors. Our own Sun is a third-generation star containing elements forged in the hearts and explosive deaths of countless stars that lived and died before it. When we look at the iron in our blood or the calcium in our bones, we are seeing atoms created inside ancient stars, cosmic recycling on the grandest scale, linking our bodies directly to the history of the universe itself. Stars form when clouds of gas and dust collapse under their own gravity. As the cloud contracts, it fragments into smaller clumps, each becoming a separate star. The most massive stars burn their nuclear fuel rapidly, shining brilliantly for just a few million years before exploding. Medium-sized stars like our Sun burn steadily for billions of years. The smallest stars, red dwarfs, sip their fuel so slowly that none has lived long enough to die since the universe began. Our Sun is roughly halfway through its 10 billion-year lifespan. In about 5 billion years, it will exhaust the hydrogen in its core and begin to expand into a red giant, eventually engulfing the inner planets, including possibly Earth. After a relatively brief phase as a planetary nebula, it will settle into retirement as a white dwarf, a dense, Earth-sized remnant that will slowly cool over trillions of years until it fades to a black dwarf, a cold, dead ember in the cosmic night. More massive stars meet more dramatic ends. Stars between 8 and 20 times the mass of our Sun explode as supernovae, briefly outshining entire galaxies before leaving behind a neutron star, a city-sized object so dense that a teaspoonful would weigh billions of tons. Stars more than 20 times as massive as our Sun collapse to form black holes, regions from which nothing, not even light, can escape. These stellar remnants, white dwarfs, neutron stars, and black holes represent the final stages of stellar evolution, the quiet afterlife of stars that once blazed with nuclear fire. But they are not merely cosmic gravestones. Neutron stars can spin hundreds of times per second, beaming radiation across space like cosmic lighthouses. Black holes can tear apart unfortunate stars that venture too close, creating brilliant flares visible across billions of light years. Even in death, stars shape the cosmos around them. At the center of nearly every large galaxy lies a supermassive black hole, millions or billions of times more massive than our Sun. These cosmic titans likely grew alongside their host galaxies, each influencing the other's development through a complex dance of gravity and radiation. When matter falls into these black holes, it can form an accretion disk that heats to millions of degrees, shining brilliantly across the electromagnetic spectrum and sometimes launching jets of particles moving at nearly the speed of light. Our own galaxy harbors a supermassive black hole called Sagittarius HE, 4 million times more massive than our Sun, yet compressed into a region smaller than our solar system. Though currently quiet, periodically swallowing only small amounts of gas and dust, it may have been much more active in the past. Evidence suggests that many galaxies go through active phases when their central black holes devour matter voraciously, shining as brilliant quasars that can be seen across billions of light years. These quasars represent some of the most luminous objects in the universe, outshining entire galaxies despite emanating from regions no larger than our solar system. They are cosmic engines of incredible efficiency, converting matter into energy with a proficiency that dwarfs nuclear fusion. The light from distant quasars has traveled for billions of years to reach us, providing glimpses of the early universe when galaxies were young and black holes were growing rapidly. In our local cosmic neighborhood, galaxies tend to cluster together, bound by mutual gravitational attraction. Our Milky Way is on a collision course with the nearby Andromeda galaxy, with the encounter expected in about 4.5 billion years. Such galactic mergers are common in the universe, driving the growth of larger structures and triggering bursts of star formation as gas clouds collide and compress. These galaxy clusters, in turn, form even larger structures, superclusters strung along the filaments of the cosmic web. The largest confirmed structure discovered so far, the Hercules Corona Borealis Great Wall, spans about 10 billion light-years, roughly a tenth of the diameter of the observable universe. These immense structures represent the largest scales over which gravity has been able to organize matter since the Big Bang. Beyond these scales, the universe appears remarkably uniform, a property cosmologists call homogeneity and isotropy. No matter which direction we look, on the largest scales, the distribution of galaxies is roughly the same. This uniformity is another legacy of cosmic inflation, which smoothed out any initial irregularities while preserving tiny quantum fluctuations as the seeds of a future structure. This uniformity extends to the laws of physics themselves, which appear to be the same throughout the observable universe. The same elements that make up stars and planets in our galaxy are found in the most distant observable galaxies. The same electromagnetic waves that carry light from distant quasars follow the same laws as those in our laboratory experiments. The gravitational force that binds our feet to Earth is the same force that shapes the cosmic web across billions of light years. But while the laws may be uniform, the future of the universe is not certain. Its fate depends on the balance between the inward pull of gravity and the outward push of dark energy. Current measurements suggest that dark energy is winning this cosmic tug-of-war, causing the expansion of the universe to accelerate rather than slow down. If this trend continues, the universe will expand forever, growing colder and darker as galaxies recede beyond each other's horizons. In this scenario, often called the Big Freeze or heat death, the universe would eventually reach a state of maximum entropy. Stars would exhaust their fuel and die, black holes would slowly evaporate through a process called Hawking radiation. Even protons, the building blocks of atoms, might eventually decay. After unimaginable eons, numbers so vast they dwarf the current age of the universe, nothing would remain but an ever-expanding void of low-energy radiation, approaching but never quite reaching absolute zero. But this is just one possible fate. If dark energy were to weaken or change its properties, gravity might eventually halt and reverse the cosmic expansion, leading to a big crunch as all matter collapses back into a state similar to the Big Bang. Or perhaps dark energy might strengthen over time, eventually becoming so powerful that it tears apart galaxies, stars, planets, and even atoms in a big rip. Or maybe the vacuum itself is unstable and a quantum fluctuation could trigger a transition to a lower energy state, changing the laws of physics in a cosmic instant, a vacuum decay that would spread at the speed of light, erasing the universe as we know it. These scenarios remain speculative, based on extrapolating current trends over timescales so vast they challenge human comprehension. The universe has been expanding for nearly 14 billion years, a mere instant compared to the trillions of years over which these ultimate fates might unfold. Our cosmic story is still in its early chapters, with most of the book yet to be written. As we float in our mind's eye through the vastness of space, we might wonder about our place in this cosmic story. Our planet Earth, a pale blue dot orbiting an ordinary star in the outskirts of an ordinary galaxy, seems insignificant against the backdrop of cosmic immensity. Yet on this tiny world, something remarkable has happened. Matter has become aware of itself. Through the emergence of life and eventually intelligence, the universe has developed the capacity to contemplate its own existence, to wonder about its origin and fate, to seek meaning in its vast, ancient expanse. This capacity for wonder, this ability to look up at the night sky and ask questions about what we see, connects us to the cosmos in a profound way. The atoms in our bodies were forged in the hearts of stars that lived and died before our sun was born. The iron in our blood, the calcium in our bones, the carbon in our cells, all were created through nuclear fusion in stellar cores or in the violent deaths of massive stars. We are, in the most literal sense, made of star stuff. Our physical existence a direct continuation of cosmic history. Moreover, the laws of physics that govern the behavior of atoms in our bodies are the same laws that shape galaxies and drive the expansion of the universe. The electromagnetic force that binds electrons to atomic nuclei is the same force that carries light across billions of light years. The strong nuclear force that holds protons and neutrons together in atomic nuclei is the same force that powered the first stars. The gravitational force that keeps our feet on the ground is the same force that forms galaxies and bends space-time around black holes. This continuity, this deep connection between the microscopic and the macroscopic, between our bodies and the cosmos, suggests that we are not separate from the universe but an integral part of it. We are the universe becoming conscious of itself, matter evolved to complexity sufficient to contemplate its own origins. Our curiosity about the cosmos is the universe's curiosity about itself. The boundary between what we know and what remains mystery shifts with each new discovery, each new observation, each new theory. The edge of knowledge is not fixed, but fluid, advancing with human ingenuity and technological progress. What seems inconceivable today may become commonplace tomorrow, just as the idea of billions of galaxies would have seemed fantastical to astronomers a century ago. Yet some questions may forever elude definitive answers. Why does the universe exist at all rather than nothing? Why do the physical constants have the values they do, allowing for the emergence of complexity and life? Is our universe unique or one of many in a vast multiverse? These questions touch not only on physics but on philosophy, on the limits of what science can address, on the boundary between knowledge and wonder. In the dance between knowledge and mystery, between what we understand and what we seek to understand, lies the continuing adventure of human engagement with the cosmos. Each answer reveals new questions, each discovery opens new horizons. The universe remains ever fascinating precisely because it is not fully known, because it continues to surprise and challenge our preconceptions, because it remains, despite all our advances, fundamentally mysterious. As you drift toward sleep tonight, let the immensity of the cosmos cradle rather than overwhelm you. The same physical laws that govern the behavior of distant galaxies also govern the rhythm of your breathing, the beating of your heart, the firing of neurons in your brain. You are not separate from the cosmic story, but an integral part of it. A conscious participant in the universe's ongoing evolution, a brief but meaningful note in its grand symphony. The infinity of space stretches in all directions, beyond the reach of our telescopes, perhaps beyond the limits of what we can ever observe. Yet infinity resides not only in the vastness of space, but in the depth of our questioning, in the endless capacity for wonder that defines our humanity. As you close your eyes, remember that the darkness behind your eyelids is filled with the same mysteries as the darkness between the stars, mysteries that invite not fear but curiosity, not despair but awe. In this darkness, we find not emptiness but potential, the same potential that permeated the early universe before the first stars ignited. The void between galaxies is not truly empty, but filled with tenuous gas, invisible dark matter, and the omnipresent cosmic microwave background radiation. Even the darkest regions of space contain at least a few atoms per cubic meter, sparse beyond imagining compared to the air we breathe, yet not the perfect vacuum we might envision. The universe abhors absolute emptiness, filling even its most barren reaches with whispers of matter and energy. This nearly empty space makes up most of the cosmos. The stars that seem so numerous in our night sky are islands of light in a vast ocean of darkness. If we could somehow shrink the sun to the size of a grain of sand, the nearest star would be over 4 miles away. Galaxies themselves are separated by millions of light years of mostly empty space. This emptiness is what allows the universe to expand without galaxies themselves growing larger. The space between cosmic structures stretches while the structures themselves remain intact, bound by their own gravity. The expansion of space itself remains one of the most profound discoveries of modern cosmology. Unlike ordinary movement through space, cosmic expansion stretches the very fabric of reality, increasing the distance between galaxies without them moving through space at all. It's as if the grid lines on a cosmic map were being slowly drawn apart, carrying galaxies along like dots on an inflating balloon. This expansion occurs everywhere at once, with no center and no edge, a concept that challenges our intuition but follows naturally from Einstein's equations of general relativity. This cosmic expansion shapes our understanding of infinity in physical reality. An infinite universe that expands forever becomes, in some sense, more infinite with time, though mathematically infinity plus any finite number remains infinity. Yet physically, the growing separation between cosmic structures creates a universe ever more dominated by emptiness, where interactions between distant galaxies become increasingly rare and eventually impossible as they recede beyond each other's. Cosmic horizons. The concept of cosmic horizons introduces another kind of boundary to our understanding, not a physical edge to the universe, but a limit to what we can observe. The particle horizon marks the maximum distance from which light could have reached us since the beginning of time, defining our observable universe. Beyond this horizon may lie more universe, possibly infinite in extent, that remains forever invisible to us, it's a light unable to reach us even given infinite time due to the accelerating cosmic expansion. This horizon is not static but dynamic. Each moment, light from slightly more distant regions reaches us for the first time, gradually expanding our observable universe. Yet paradoxically, as cosmic expansion accelerates, there are regions whose light, though visible to us today, will eventually fade from view as those regions recede beyond our horizon. The observable universe of the distant future will be smaller than it is today, limited to those galaxies bound together by gravity into local clusters. When we speak of the edge of the observable universe, we refer not to a wall or barrier, but to a temporal boundary, the limit of how far back in time we can see. The most distant light reaching our telescopes shows the universe as it was just a few 100,000 years after the Big Bang, when it first became transparent to radiation. Before this epoch, the universe was an opaque plasma, too hot and dense for light to travel freely. This cosmic dawn represents the earliest moment we can directly observe, a baby picture of our universe when it was less than 100,000th of its current age. Yet cosmologists can infer what happened even earlier through subtle patterns imprinted on this ancient light and through theoretical models grounded in particle physics. The very early universe experienced a period of exponential expansion called cosmic inflation, when space itself stretched faster than the speed of light. This inflationary epoch lasted only a tiny fraction of a second but increased the size of the universe by a factor of at least 10 to the power of 26, expanding quantum scale fluctuations into the seeds of today's cosmic structures. Inflation solves several cosmic puzzles, explaining why the universe appears so uniform in all directions and why its geometry is so precisely flat. But it also suggests something remarkable about cosmic origins. Our entire observable universe may have originated from a region smaller than an atomic nucleus. The vastness we observe today was once unimaginably tiny, containing all the energy that would later form every galaxy, star, planet, and living being. This inflationary paradigm has led some cosmologists to propose the concept of eternal inflation, where our universe might be just one bubble in an eternally inflating multiverse. In this scenario, inflation ends in some regions, forming pocket universes like our own while continuing forever in others. These other pocket universes might have entirely different physical laws, different constants of nature, different dimensions of space and time, an infinity of possibilities playing out across an infinity of cosmic domains. Such ideas take us to the very frontier of theoretical physics, where mathematics, philosophy, and empirical science blur together. These multiverse theories are not mere speculation, but emerge naturally from the same physics that successfully explains our observable cosmos. Yet they raise profound questions about what we mean by universe and whether the concept of infinity applies not just to space and time, but to possibility itself. Even within our observable universe, infinity manifests in the concept of quantum uncertainty. At the smallest scales, reality becomes probabilistic rather than deterministic. Particles exist in multiple states simultaneously until measured, with their positions and momenta described by probability distributions rather than definite values. This fundamental uncertainty, enshrined in Heisenberg's uncertainty principle, suggests that perfect knowledge of the universe is impossible even in principle. There will always be aspects of reality that remain veiled in probability clouds. This quantum uncertainty played a crucial role in cosmic origins. In the earliest moments after the Big Bang, quantum fluctuations, tiny variations in energy density, were stretched to cosmic scales by inflation, creating the slight irregularities that would eventually become galaxies and galaxy clusters. What began as microscopic variations subject to the strange rules of quantum mechanics became the vast cosmic web we observe today. Our existence depends on this quantum uncertainty. Without it, the universe would be perfectly uniform, with no structures to form stars, planets, or living beings. Quantum mechanics also introduces the concept of virtual particles, pairs of particles and antiparticles that briefly pop into existence from the vacuum before annihilating each other. These ephemeral particles are not merely theoretical constructs, but have measurable effects, influencing the properties of real particles and contributing to what physicists call vacuum energy. This vacuum energy may be related to dark energy, the mysterious force accelerating cosmic expansion, suggesting that even empty space contains hidden energy and is alive with quantum activity. Near black holes, these virtual particles take on special significance. When they form near the event horizon, the point of no return, surrounding a black hole, one particle may fall in while the other escapes, carrying away a tiny amount of the black hole's energy. Through this process, known as Hawking radiation, black holes slowly evaporate, eventually disappearing completely after unimaginable eons. Even these cosmic devourers, whose gravitational pull is strong enough to trap light itself, are not immune to the subtle effects of quantum mechanics. Black holes represent another manifestation of infinity in our universe. At their centers, our current theories predict singularities, points where matter is compressed to infinite density and space-time is infinitely curved. These singularities mark the breakdown of general relativity, suggesting the need for a quantum theory of gravity to fully understand what happens in these extreme conditions. Perhaps true infinities do not exist in nature, and some yet undiscovered physical principle prevents matter from being compressed beyond a certain density. Do event horizons surrounding black holes act as cosmic veils, hiding these potential infinities from the rest of the universe? According to Einstein's relativity, an observer falling into a black hole would cross the event horizon without noticing anything unusual, continuing their journey toward the central singularity. But to an outside observer, this infalling traveler would appear to slow down, their image growing fainter and redder, but never quite reaching the horizon. This stark difference in perspectives highlights how space-time itself warps near these cosmic monsters, challenging our intuitive notions of space and time. The most massive black holes reside at the centers of galaxies, including our own Milky Way. These supermassive black holes, millions or billions of times more massive than our Sun, likely grew alongside their host galaxies in a cosmic dance of mutual influence. When matter falls into these giants, it forms an accretion disk that heats to millions of degrees, shining brilliantly across the electromagnetic spectrum and sometimes launching jets of particles, moving at nearly the speed of light. These active galactic nuclei can outshine the combined light of all the stars in their galaxies, visible across billions of light-years of cosmic distance. Our own galaxy's central black hole, Sagittarius Ia, is relatively quiet by these standards, accreting material at a modest rate. Yet it still influences the motion of stars in the galactic center, with some stars orbiting it at speeds of thousands of kilometers per second. By tracking these stellar orbits with precision, astronomers have determined that this invisible object contains the mass of about 4 million suns compressed into a region smaller than our solar system, compelling evidence for its identification as a supermassive black hole. The discovery of gravitational waves, ripples in space-time predicted by Einstein's general relativity, has opened a new window on black holes and other compact objects. When black holes or neutron stars spiral together and merge, they generate powerful gravitational waves that travel across the cosmos at the speed of light. These waves stretch and compress space itself by tiny amounts, less than the width of an atomic nucleus over a distance of several kilometers. Yet sophisticated detectors like LIGO and Virgo can measure these minuscule distortions, allowing us to hear these cosmic collisions even when they occur in regions hidden from traditional telescopes. These gravitational wave detections have confirmed that black holes of various sizes, from a few times the mass of our Sun to dozens of solar masses, are common in the universe, forming from the collapsed cores of massive stars. They have also revealed that neutron stars, the ultra-dense remnants of stellar explosions, where a mass greater than our Sun is compressed into a sphere the size of a city, can collide and merge, producing not only gravitational waves but also flashes of light across the electromagnetic spectrum and creating many of the heaviest elements in the periodic table, including gold and platinum. The space between stars within galaxies is not empty but filled with gas, dust, and cosmic rays, high-energy particles accelerated by supernovae and other violent cosmic events. This interstellar medium is the source of the raw material for new stars, arranged in clouds that can span dozens or even hundreds of light years. In regions where these clouds become particularly dense, gravity overcomes the outward pressure of gas, causing the cloud to collapse and fragment into nascent stars. These stellar nurseries appear as nebulae, colorful, glowing regions visible in astronomical images, where the cycle of stellar birth, life, and death continues. Stars themselves are cosmic engines, converting hydrogen into helium through nuclear fusion in their cores, releasing energy that ultimately radiates as light and heat. This nuclear fusion process is the source of almost all the energy that sustains life on Earth, captured by plants through photosynthesis and flowing through the food web to all living organisms. The warmth you feel on your skin on a sunny day is the product of fusion reactions occurring in the Sun's core 8 minutes earlier, their energy carried across 93 million miles of space as photons, particles of light. The lightest elements, hydrogen and helium, formed in the first few minutes after the Big Bang, when the entire universe was hot enough to function as a nuclear fusion reactor. But all heavier elements were forged inside stars or in their explosive deaths. Carbon, the backbone of all known life, forms in the cores of aging stars through the triple alpha process, where 3 helium nuclei fuse to form a carbon nucleus. Oxygen forms when carbon captures another helium nucleus. These and other elements are scattered into space when stars die, enriching the interstellar medium and providing the ingredients for new stars, planets, and eventually life. This process of stellar nucleosynthesis connects us directly to the cosmos. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were created inside stars that lived and died before our Sun was born. As the astronomer Carl Sagan famously noted, we are made of star stuff, our physical existence a direct continuation of cosmic evolution. The atoms in your body have existed for billions of years, cycling through stars, interstellar clouds, and now temporarily arranged in the complex pattern that is you. The arrangement of these atoms into complex, self-replicating structures represents another kind of infinity, the near-infinite variety of forms that matter can take under suitable conditions. From simple organic molecules to the intricate machinery of living cells, from single-celled organisms to the vast diversity of multicellular life, from instinctive behavior to conscious thought capable of contemplating the universe itself, this progression represents an open-ended exploration of possibility, limited only by the constraints of physics and chemistry and the selective pressures of evolution. Intelligence itself, the capacity to model the world, predict future states, and act accordingly, may be the universe's way of understanding itself. Through the emergence of conscious beings, the cosmos has developed the ability to contemplate its own existence, to discover the laws that govern its behavior, to trace its history from the Big Bang to the present day. We are the universe becoming aware of itself, matter evolved to complexity sufficient to wonder about its origins and destiny. This cosmic perspective reveals our deep connection to the universe and to each other. The hydrogen atoms in water molecules throughout your body were created in the Big Bang itself, nearly 14 billion years ago. The carbon atoms in your DNA were forged in the cores of ancient stars. We are all, literally, made of the same star stuff, our physical substance traceable to the same cosmic origins. In this sense, the boundary between self and universe is more permeable than we might imagine. Our bodies, temporary arrangements of atoms that have existed since near the beginning of time and will continue to exist long after we are gone. Yet we are more than just collections of atoms. The patterns of information, the relationships between particles, the emergent properties of complex systems, these less tangible aspects of reality are equally fundamental. Consciousness, perhaps the greatest mystery we can contemplate, emerges from the intricate dance of neurons in our brains, their connections forming patterns of staggering complexity. How subjective experience arises from this physical substrate remains one of the deepest questions in science and philosophy, touching on the nature of reality itself. As we ponder these profound questions, we might wonder whether other conscious beings exist elsewhere in the cosmos, contemplating similar mysteries beneath different stars. The sheer vastness of the universe, with hundreds of billions of galaxies, each containing hundreds of billions of stars, suggests that Earth is unlikely to be the only world where life has emerged. Recent discoveries of thousands of exoplanets orbiting other stars, many with potentially habitable conditions, further support this possibility. Yet, despite the probable abundance of planets, the emergence of life, particularly complex intelligent life, may be rare. The evolutionary path from single cells to multicellular organisms, from simple nervous systems to brains capable of abstract thought, involves many contingent steps, each with no guarantee of success. The physicist Enrico Fermi recognized this paradox. If intelligent life is common in the universe, where is everyone? The silence of the cosmos, the absence of clear signals from other civilizations, suggests that either intelligent life is rarer than we might hope, or that interstellar communication and travel present barriers we have yet to overcome. This Fermi paradox has many potential resolutions, ranging from the sobering intelligent life tends to destroy itself shortly after developing advanced technology to the hopeful the galaxy teems with life, but civilizations wisely observe rather than interfere with developing worlds like our own. Perhaps we are simply early arrivals on the cosmic scene, among the first generations of intelligent life in a universe that will exist for trillions of years to come. Or perhaps life takes forms so different from our own that we would not recognize it, even if we were looking directly at it. The possibility of extraterrestrial life reminds us that our perspective is limited not only by the boundaries of our observable universe, but by the constraints of our biology, our technology, and our imagination. What we can perceive directly, visible light, audible sound, tangible objects, represents a tiny slice of what exists. Our scientific instruments extend our senses, allowing us to detect radio waves, X-rays, infrared light, ultrasonic vibrations, and subatomic particles. Yet even with these tools, our understanding remains partial, our knowledge provisional, our exploration of cosmic reality ongoing and incomplete. This incompleteness is not a failure but a feature of the cosmic adventure, an invitation to continue the discovery, to the expansion of knowledge beyond current horizons. The history of astronomy is a series of horizon expansions, from the naked eye observations of ancient sky watchers to the sophisticated space telescopes of today. Each new instrument, each new theory, each new perspective reveals aspects of the cosmos previously hidden or misunderstood. The universe is not just vast in spatial extent, but in the depth of its mystery, in the layers of reality waiting to be uncovered. Consider dark matter, a substance that neither emits nor absorbs light, yet makes up roughly 85% of all matter in the universe. We know it exists because of its gravitational effects. Galaxies rotate too quickly, galaxy clusters hold together too tightly, and cosmic structures form too rapidly for visible matter alone to explain. Yet, despite decades of searching, we have not directly detected dark matter particles or determined their nature. They pass through our bodies constantly, invisible and untouchable, their presence known only through their subtle influence on cosmic structures. Similarly, dark energy, the mysterious force accelerating the expansion of the universe, makes up roughly 68% of the total energy content of the cosmos. Discovered only in 1998 through observations of distant supernovae, dark energy remains one of the greatest puzzles in modern physics. It may be a property of empty space itself, a vacuum energy inherent in the fabric of reality. Or it may be something more exotic, a new field or force not yet incorporated into our physical theories. Either way, most of the universe consists of substances whose fundamental nature remains unknown. These cosmic mysteries remind us of the vastness not just of space, but of potential knowledge, the gap between what we currently understand and what remains to be discovered. Each answered question tends to raise new ones, each solved puzzle reveals new mysteries. The frontier of knowledge is not a fixed boundary but an ever-advancing horizon, receding as we approach it, revealing new landscapes beyond. This infinite potential for discovery is, perhaps, the truest infinity we encounter in our cosmic exploration. As you drift closer to sleep, consider that the darkness surrounding you is not empty but full of possibility, of unseen wonders, of mysteries waiting to be unraveled. The night sky above, though hidden by walls and ceiling, contains not just stars and galaxies, but questions about the nature of reality, the origin of the cosmos, the meaning of existence. These questions have engaged human minds for thousands of years, across cultures and civilizations, connecting us through our shared curiosity about the universe we inhabit. The ancient Greeks conceived of the cosmos as a harmonious, ordered whole, the root of our word cosmetic, suggesting beauty and arrangement. They saw planetary motions as expressions of mathematical perfection, spheres within spheres rotating with divine precision. The Maya tracked Venus and other celestial bodies with remarkable accuracy, creating calendars that synchronized human activities with cosmic cycles. Chinese astronomers recorded supernovae and comets, interpreting them as heavenly omens affecting earthly affairs. Across the Pacific, Polynesian navigators used their intimate knowledge of the night sky to voyage thousands of miles across open ocean, finding tiny islands without modern instruments. These diverse traditions share a recognition of human embeddedness in a larger cosmic context, a relationship not just of observation but of participation. We are not merely spectators of the cosmic drama, but actors within it, our bodies composed of elements forged in stellar furnaces, our actions governed by the same physical laws that shape galaxies and govern the expansion of the universe. The boundary between us and cosmos is permeable, a continuum rather than a sharp divide. This continuity extends to time as well as space. The light from distant galaxies carries information from the ancient past, a cosmic time capsule allowing us to observe directly how the universe looked billions of years ago. The cosmic microwave background radiation provides a snapshot of the universe when it was just 380,000 years old, less than 100,000 of its current age. These observations connect us to cosmic history, allowing us to reconstruct the evolutionary arc from the Big Bang to the complex structures we observe today. But the cosmic story extends into the future as well, unfolding according to the same physical principles that have governed its past. Stars will continue to form from collapsing clouds of gas and dust, shine for millions or billions of years, and eventually die. Some quietly as white dwarfs, others spectacularly as supernovae or black holes. Galaxies will continue to evolve, some merging with their neighbors, others receding beyond cosmic horizons as the universe expands. New planets will form around new stars, perhaps giving rise to new forms of life, new kinds of consciousness, new perspectives on cosmic reality. The time scales of these future events dwarf human history. Our sun will continue to shine for about 5 billion more years before exhausting the hydrogen in its core and expanding into a red giant. The Milky Way and Andromeda galaxies will collide in about 4.5 billion years, their stars mostly passing safely by one another, but their combined gas igniting new episodes of star formation. In about 100 trillion years, the last stars will exhaust their fuel, leaving a universe of stellar remnants, white dwarfs, neutron stars, and black holes slowly cooling in an ever-expanding void. Even these stellar remnants are not eternal. White dwarfs will cool to black dwarfs over quadrillions of years. Neutron stars will eventually decay. Black holes will slowly evaporate through Hawking radiation, with the smallest disappearing first and the most massive, supermassive black holes persisting for up to 10 to the power of 100 years, a number so vast it dwarfs the current age of the universe by a factor of 10 billion trillion. After the black holes evaporate, the universe will contain only low-energy photons, neutrinos, and other fundamental particles, spread ever more thinly across ever-expanding space. This heat death represents the end of structure as we know it, the final dissipation of all available energy, the ultimate triumph of entropy over complexity. Yet even this is not necessarily the absolute end. Quantum fluctuations might, given enough time, give rise to new structures, new complexity, perhaps even new universes budding from the void of the old. These vast timescales challenge our imagination, just as the vast spatial scales of the cosmos challenge our intuition. We are adapted to perceive and understand phenomena on the scale of human bodies, human lifespans, human societies. Yet, through mathematics, through scientific instruments, through logical inference and theoretical modeling, we can extend our understanding beyond these natural limits, grasping, however imperfectly, realities that exceed direct experience. This capacity to transcend our perceptual limitation, to understand phenomena we cannot directly observe, represents one of the most remarkable aspects of human consciousness. We can contemplate particles too small to see, timescales too vast to witness, spaces too large to traverse, forces too subtle to feel. We can model the interior of a star, the early moments of the universe, the event horizon of a black hole. Though physically tiny on the cosmic scale, our minds can encompass the entire observable universe and speculate about what lies beyond. This cognitive vastness mirrors the spatial vastness of the cosmos, suggesting a kind of infinity nested within the finite physical structures of our brains. The capacity for abstract thought, for imagination, for the construction of theoretical models unbound by immediate sensory experience, these mental abilities create an inner space potentially as rich and varied as the outer space of astronomy. The universe is not just out there, but also in here, reflected and reconstructed in our understanding, our theories, our mental models of reality. This inner cosmos, this mental reconstruction of physical reality, is not isolated but shared through language, through mathematics, through art and culture. When you read about the expanding universe or the birth of stars, these concepts take shape in your mind, creating an internal representation that, while necessarily simplified, captures essential aspects of cosmic reality. This sharing of mental models creates a kind of collective understanding, a cultural cosmos that evolves as our knowledge grows, as new observations refine our theories, as new perspectives reveal previously overlooked aspects of reality. The language we use to describe the cosmos shapes our understanding of it. The metaphors we employ, the fabric of space-time, the birth of stars, the death of the universe, translate abstract physical concepts into terms derived from a human experience. These metaphors are both useful and limiting, enabling understanding while potentially constraining imagination. The challenge is to recognize them as tools rather than literal descriptions, as bridges between human cognition and cosmic reality rather than perfect representations of that reality. Mathematics offers a more precise language, one less bound to human sensory experience. The equations of general relativity describe curved space-time without requiring us to visualize four-dimensional geometry. The wave functions of quantum mechanics capture particle behavior without forcing us to resolve the wave-particle duality in familiar terms. These mathematical formalisms extend our conceptual reach beyond the limits of ordinary language, allowing us to model aspects of reality that defy straightforward verbal description. Yet even mathematics has its limits. Gödel's incompleteness theorems demonstrate that any consistent mathematical system, complex enough to describe the natural numbers, will contain truths that cannot be proven within that system. This result suggests a kind of horizon to formal knowledge, a boundary beyond which lies truth that cannot be captured in axioms and proofs. Perhaps reality itself exceeds the descriptive power of any formal system, containing aspects that can be approached but never fully captured by our theories. This possibility does not diminish the value of scientific and mathematical understanding, but places it in context as an ongoing, open-ended exploration rather than a march toward complete knowledge. The cosmos may be not just materially infinite, but conceptually inexhaustible, containing depths that can be plumbed forever without reaching bottom. Each discovery, each theoretical advance, each new observation reveals new aspects of reality while simultaneously raising new questions, new possibilities, new horizons for exploration. This inexhaustibility applies not just to the external universe, but to our inner experience of it. The beauty of a starry night sky, the wonder of contemplating cosmic distances, the intellectual excitement of grasping a new theoretical insight. These subjective experiences are as real as the physical phenomena they respond to, as much a part of cosmic reality as stars and galaxies. Consciousness itself, perhaps the most profound mystery we encounter, emerges from physical processes yet seems to transcend them, creating meaning and value not reducible to particles and forces. As you hover on the edge of sleep, consider that your consciousness, your capacity to perceive, to think, to wonder, is itself a cosmic phenomenon, arising from the same evolutionary processes that shaped all life on Earth, built from elements forged in ancient stars, governed by the same physical laws that shape the cosmos. Your dreams, soon to unfold in the theater of your sleeping mind, represent another kind of reality, subjective rather than objective, personal rather than universal, yet no less remarkable for being ephemeral. In these transitional moments between wakefulness and sleep, the boundary between inner and outer reality softens. Thoughts drift like cosmic dust, gradually coalescent into the structures of dreams. Time stretches and contracts, no longer bound to the steady rhythm of clocks. Space becomes malleable, locations shifting and merging according to emotional rather than physical logic. This dream space, though created by your brain, has its own kind of infinity, an unbounded realm of possibility, limited only by the architecture of your mind and the residue of your experiences. The transitions between cosmic epochs mirror this shift from wakefulness to dreaming. The early universe, hot and dense, abounded with energy but lacked structure, a state of pure potential not yet realized in distinct forms. As it cooled and expanded, this primordial plasma differentiated into distinct particles, then atoms, then molecules, then stars and galaxies. Structure emerged from uniformity, complexity from simplicity, diversity from unity. Yet this emergence was not imposed from outside but unfolded according to the inherent properties of matter and energy, the natural consequences of physical law. Similarly, your consciousness did not arise fully formed but emerged gradually from simpler precursors, the biochemical reactions of single cells, the simple nervous systems of early animals, the increasingly complex brains of mammals, primates, and, finally, humans. Your own awareness developed from the reflexive responses of infancy to the self-reflective cognition of adulthood. Like the cosmos, consciousness evolves from simplicity to complexity, from undifferentiated potential to articulated structure. This parallel between cosmic and conscious evolution is not merely poetic but reflects a deeper principle. Complex systems, whether physical or mental, often display similar patterns of self-organization, of structure, emerging from interactions among simpler components. Galaxies form from the gravitational attraction of countless atoms, Consciousness emerges from the electrochemical signaling of billions of neurons, both manifesting order and pattern at scales far larger than their constituent elements. These emergent phenomena cannot be fully predicted from or reduced to their components. The whole is not just the sum of its parts, but includes the relationships between those parts, the dynamic patterns that arise from their interactions. A single water molecule is not wet. Wetness emerges only from the collective behavior of many molecules. A single neuron is not conscious. Consciousness emerges only from the coordinated activity of neural networks. Similarly, a single atom does not make a galaxy. Galactic structures emerge only from the collective gravitational influence of countless atoms. This emergence of complexity from simplicity, of order from chaos, represents a counterbalance to the universe's overall trend toward increasing entropy, the gradual dissipation of energy, the increasing disorder of closed systems over time. While the universe as a whole becomes more disordered, local pockets of order can form and persist, from galaxies and stars to planets and living beings. These islands of complexity, these temporary reversals of the entropic trend, are made possible by energy flows, the conversion of gravitational potential into heat and light in stars, the capture of stellar energy by plants, and conversion into the chemical energy that powers all life on Earth. Your own existence exemplifies this principle. Your body maintains its complex order by consuming energy from food, ultimately derived from sunlight, using this energy to counteract the tendency toward disorder that would otherwise lead to dissolution. This maintenance of order requires constant energy input. When that input ceases at death, entropy quickly reasserts itself, complexity unravels, and the atoms that temporarily composed your body return to simpler arrangements, eventually recycled into new forms, new structures, new participants in the cosmic dance. This continuous recycling of matter connects all things in a grand cycle of cosmic evolution. The iron atoms in your blood once formed part of ancient stars that exploded billions of years ago, scattering their elemental bounty across space. The carbon atoms in your cells once floated in interstellar clouds before condensing into the solar nebula that formed our sun and planets. The hydrogen atoms in the water molecules throughout your body date back to the Big Bang itself, nearly 14 billion years ago. Nothing is truly lost, merely transformed, rearranged, incorporated into new patterns. This material continuity extends to energy as well. The sunlight that warms your skin represents energy released by nuclear fusion in the sun's core, converted to electromagnetic radiation that travels 93 million miles through space. Plants capture this energy through photosynthesis, converting it to chemical form. Animals eat plants or other animals, transferring this stored energy up the food chain. Your every movement, your every thought, your very consciousness is powered by this transformed stellar energy, connecting your existence directly to cosmic processes. The universe thus reveals itself not as a collection of isolated objects, but as a web of relationships, a network of connections spanning scales from the subatomic to the supergalactic. Nothing exists in isolation. Everything participates in multiple overlapping systems, influencing and being influenced by countless other entities. A star's gravitational field shapes the orbits of its planets. Those planets' gravitational fields shape the trajectories of their moons. Those moons raise tides on their planets, and so on in an endless chain of mutual influence. This interconnectedness applies not just to physical systems but to knowledge itself. Astronomy depends on physics. Physics depends on mathematics. Mathematics depends on logic. Logic depends on consistent patterns of thought. Each field illuminates the others, each perspective reveals aspects of reality invisible from other viewpoints. The cosmos is comprehensible not through any single approach, but through the integration of diverse ways of knowing, from the quantitative precision of science to the experiential richness of direct observation, from the logical rigor of mathematics to the pattern recognition of intuition. As your consciousness drifts toward sleep, these different modes of understanding may begin to merge and blend. The boundary between analytical thought and intuitive recognition softens. Connections appear spontaneously, patterns emerge unbidden. This liminal state, neither fully awake nor fully asleep, offers its own kind of insight, its own approach to knowledge. Ideas that seemed separate while fully awake reveal their hidden relationships. Concepts that seemed clear become fluid, morphing into new forms, suggesting new possibilities. In this twilight consciousness, you may glimpse the cosmos not as an object of study but as a lived reality, not as something separate from yourself, but as something you participate in directly, not as a collection of facts, but as an ongoing process, of which you are an integral part. This perspective, sometimes called the overview effect when experienced by astronauts viewing Earth from space, reveals the artificial nature of the boundaries we often draw between self and world, between humanity and nature, between life and its cosmic context. From this vantage point, the question of whether the universe is infinite takes on a different character. Beyond the mathematical concept of infinity, beyond the astronomical question of spatial boundlessness, lies the experiential infinity of the present moment, the inexhaustible depth of now, the endless richness of immediate experience. Each moment contains the entire cosmos as it exists. Then, each perspective reveals a unique facet of universal reality. Each conscious experience manifests a singular expression of cosmic possibility. This experiential infinity complements rather than contradicts the spatial and temporal vastness revealed by astronomy. Just as the universe extends outward in space beyond our ability to observe, it extends inward in complexity beyond our ability to fully comprehend. Just as cosmic history stretches backward in time to the Big Bang and forward to the distant future, our subjective experience unfolds in an eternal present, neither past nor future but always now. These different infinities, outward, inward, backward, forward, objective, subjective, intertwine and interpenetrate, distinct yet inseparable aspects of a single reality. As sleep approaches, you may find these distinctions dissolving, these boundaries blurring. The mental cosmos of thought and imagination merges with the physical cosmos of stars and galaxies. The subjective experience of consciousness blends with the objective reality it perceives. The finite human perspective opens to the infinite cosmic context, not losing itself but finding itself more fully in this expanded awareness. This dissolution of artificial boundaries, this recognition of fundamental unity represents not confusion but clarity, a direct apprehension of the wholeness that intellectual analysis necessarily fragments. In this wholeness, the cosmos reveals itself as both knowable and mysterious, both comprehensible and inexhaustible. The same physical laws that govern falling apples also shape galactic structures. The same mathematical principles that describe geometric shapes also model cosmic expansion. The same evolutionary processes that produced all life on Earth also generated the capacity to comprehend those processes. The universe is not alien or other, but our deepest home, not a collection of objects, but a communion of subjects, not a problem to solve, but a reality to participate in. This participation takes many forms, from the direct sensory experience of stargazing to the abstract conceptual understanding of cosmological theory, from the emotional response to cosmic beauty to the ethical implications of recognizing our embeddedness in natural systems. Each approach reveals different aspects of cosmic reality. Each perspective contributes to a more complete understanding. The scientist measuring cosmic microwave background radiation, the poet contemplating the night sky, the child asking why the moon changes shape, all engage with the same cosmos, all contribute to humanity's ongoing relationship with its universal context. As consciousness fades into sleep, these diverse modes of engagement may seem to converge, revealing their common ground in wonder, the recognition that existence itself, consciousness itself, the cosmos itself, represents an astonishing gift, an improbable marvel, a source of perpetual amazement. This wonder persists whether we conceive the universe as finite or infinite, as eternal or bounded in time, as singular or plural. The simple fact that anything exists at all, that complexity has emerged from simplicity, that consciousness has a reason to contemplate its own origins, these remain sources of awe regardless of which cosmological model proves most accurate. In this sense, the question of cosmic infinity points beyond itself to questions of meaning and value. Whether space extends forever or curves back on itself, whether time has a beginning or is cyclical, whether our universe is unique or one of many, these cosmological questions matter not just for their scientific answers, but for what they reveal. About our place in the grand scheme, about the context of our existence, about the nature of reality itself. They are scientific questions with philosophical implications, mathematical puzzles with existential resonance. These questions accompany you into sleep, not as problems demanding immediate solutions, but as companions on the journey of understanding, as threads in the tapestry of wonder that connects all conscious beings to the cosmos they inhabit. As your awareness transitions from the waking world to the dream world, these cosmic mysteries transform as well, their abstract conceptual form giving way to symbolic and narrative expressions, their logical structure yielding to the associative logic of dreams. Yet they remain present, woven into the fabric of your sleeping mind, contributing to the rich tapestry of your unconscious experience. In this transition, you participate in one of the fundamental rhythms of cosmic existence, the alternation between activity and rest, between expansion and contraction, between complexity and simplicity. Just as the universe cycles between periods of structure formation and periods of dissolution, between the condensation of matter into stars and galaxies and its dispersal through stellar winds and supernovae, so too does consciousness cycle between the structured awareness of waking life and the fluid, boundary-dissolving experience of sleep and dreams. This rhythm extends across scales, from the daily cycle of waking and sleeping to the annual cycle of seasons, from the multi-million-year cycle of stellar lifetimes to the trillion-year cycle of galactic evolution, from the 14-billion-year history of our observable universe to the potential eternity of the multiverse. Each cycle represents not a mere repetition but a spiral, returning to similar states while simultaneously evolving, maintaining pattern while introducing variation. This combination of continuity and change, of familiarity and novelty, characterizes both cosmic and conscious evolution. As you drift into deeper sleep, these cosmic rhythms may express themselves in the cadence of your breathing, in the circulation of your blood, in the firing patterns of your neurons. Your body, though seemingly separate from the cosmos, remains intimately connected to it, synchronized with its cycles, composed of its elements, governed by its laws. The boundary between you and not you, between organism and environment, between human and cosmos, reveals itself as permeable, as conventional rather than absolute, as a useful distinction rather than an insurmountable divide. In the depths of sleep, as conscious awareness gives way to the unconscious processes of dreaming and restoration, you continue to participate in the cosmic dance, your body and mind enacting patterns established over billions of years of evolution. Your very existence a testament to the universe's capacity to generate and sustain complexity. Though your conscious awareness of the cosmos fades, your cosmic nature remains, your embeddedness in universal processes undiminished, your participation in cosmic reality uninterrupted. This continuity persists through the night, through the rhythms of REM and non-REM sleep, through the cycles of dreaming and deep rest. Even as your conscious mind relaxes its grasp on waking reality, your body continues its intricate dance of self-maintenance, your brain continues its processing of information and experiences, your existence continues as a local manifestation of cosmic processes that extend across space and time. You remain a participant in the universe even when not consciously aware of it, just as you remain influenced by gravity even when not thinking about it. As morning approaches and consciousness gradually returns, you may briefly hover in a state similar to the one you now enter, a liminal awareness, neither fully asleep nor fully awake, where the boundaries between dream and reality, between self and world, between finite and infinite, remain fluid and permeable. In this transitional state, you may momentarily glimpse again the fundamental unity underlying apparent diversity, the cosmic wholeness that intellectual analysis necessarily fragments, the seamless continuity between your individual existence and the universal context that contains and constitutes it. But for now, let yourself release into the embrace of sleep, carried by the same cosmic currents that move the stars, sustained by the same forces that bind atoms into molecules, connected to the same reality that extends, perhaps infinitely in all directions. Whether the universe itself has boundaries or extends forever, whether time had a beginning or always existed, whether reality is singular or plural, these questions will wait for waking consciousness. They have persisted for thousands of years of human inquiry. They will remain when you wake. In this moment, as consciousness gently dissolves into sleep, perhaps there is a kind of answer, not in words or equations, not in theories or models, but in the direct experience of being simultaneously finite and infinite, simultaneously individual and universal, simultaneously a distinct entity and an inseparable part of the cosmic whole. In this experience, the question transforms from an intellectual puzzle to a lived reality, from something to figure out to something to participate in, from a problem seeking solution to a mystery inviting contemplation. Rest now in this mystery, in this wonder, in this cosmos that is both your home and yourself. Sleep as the stars shine, as planets orbit, as galaxies turn, participant in the grand rhythm of a universe that continues its dance whether observed or not, whether understood or not, whether bounded or boundless. The infinity of space, the eternity of time, the inexhaustibility of reality, these remain, embracing your finite form, contextualizing your temporary existence, connecting your brief awareness to the cosmic story that precedes and follows it, that contains and constitutes it, that expresses itself through it. In this gentle surrender to sleep, you enact a cosmic truth, that boundaries dissolve, that separateness is illusion, that participation precedes observation. You do not need to understand infinity to participate in it, just as you do not need to understand dreaming to dream. Let go of the questions, release the search for definitive answers, allow yourself to be carried by the mystery rather than trying to solve it. The cosmos holds you whether comprehended or not, whether measured or unmeasured, whether named infinite or finite. As consciousness fades, as thoughts disperse like interstellar clouds, as awareness softens like the boundary between sea and sky at dusk, remember that nothing is truly lost, merely transformed, rearranged, incorporated into new patterns. Your conscious thoughts become unconscious processes, your focused attention becomes diffuse awareness, your waking cognition becomes dream logic. This transformation mirrors the cosmic recycling of matter and energy, the continuous conversion of one form into another that characterizes the universe at all scales. Sleep now, finitely being in an infinite cosmos, temporary arrangement of eternal elements, local expression of universal principles. Rested in the knowledge, or perhaps the faith, that the mystery continues even when not actively contemplated, that wonder persists even when not consciously experienced, that the cosmic dance goes on even when you are not watching. The stars will still shine, the galaxies will still turn, the universe will still expand, maintaining its ancient rhythms through the hours of your sleep, ready to be rediscovered when consciousness returns with the morning light. Good night, cosmic traveler. Sweet dreams.